Greetings, ladies and gentlemen. Welcome to today's lesson about vector transformations. So I don't know if you've seen these things before, but they're called matrices. And if you have seen them before, try not to hyperventilate. Take a few slow, deep breaths and try not to work yourself up too much about these matrices. You're not going to have to do row operations. We're not solving a system with them. We're just using them to transform a vector. So, step one in dealing with matrices is don't panic. That's important. But to kind of give you an overview of what this lesson is about is, we have these these vector things. Like you can have a vector like 3, -5. Well, this can get transformed. Like, you can rotate it 90 degrees around the origin. You can dilate by a factor of 10. Those transformations we've done previously, you can also do to vectors. Well, to do that, you're going to use a matrix. And if you're looking at your notepaper, hopefully you're looking at your notepaper, you should be, because this tells you the matrices you're going to have to know and the transformations you got to be able to do to vectors. And this has the answers for what matrices do what transformations and what it does to the components of your vector. And so at the bottom of this paper there are 4 examples. We're going to work through those examples so you can see them in action and you can see how it's doing the transformations. So before we do that, we're going to do a quick multiplication review with matrices. A quick recap is, if you have a matrix and you're timesing by another matrix, you got to take the rows of the first one and times by the columns of the second one. So if I take my row here and times by my column, it's going to be -2 times 4 and then -5 times 2, and you'll add those together, and that'll give you the first item in your new matrix. And then you're going to take your row of your first one and times by the other column, which will give you -2 times -2 and -5 times -1. And if you multiply those together and then add up those products, you'll get your new second term of your resulting matrix. So you multiply the things together, you get -8 and -10. Multiply those parts together, you'll get 4 and 5. Add them together, you'll get -18 and 9. So remember, rows are the first times the columns of the second one. And it's almost like you turn this on its side, and then you're timesing those things together. Kind of like that, but anyway. Let's go through some of the examples that are on the bottom of your little note paper here. Let's start with example 1. We need to take this vector and times by this matrix. So a vector doesn't look like a matrix, but it actually is. If you just turn that bracket into a square bracket there, instead of the vector one, and then get rid of your comma, ta-da! It is now a matrix of -2, 5. And we're going to multiply it by this matrix. So I'm going to take this row of my first matrix and times by the first column of my second one, and that'll give me -2 times -1 plus 5 times 0, right? The -2 and -1 and the 5 and 0 times together, and then you'll add those products. And then let's go to the first row of my first matrix, and then the second column. So the -2 and the 0 and the 5 and the 1 multiply together. -2 times 0 plus 5 times 1. And that'll give me my resulting matrix. -2 times -1 is 2. 5 times 0 is 0. And then -2 times 0 is 0. And then 5 times 1 is 5. And now we're left with 2, 5, like this. And if you remember, this came from a vector up here, which we just, changed its brackets on the end. So let's change them back so it looks like a vector again, 2, 5. Well, we have changed this vector by timesing by this matrix in a very specific way. It looks like -2 became +2, and then 5 became 5 still. And so look at your little note paper and figure out which transformation keeps the numbers in the same order. We still got 2, 5, and 2, 5, but it changed the sign on the x. So look through here, let's see, which one just changes the sign on the x-ray. Well, that's down here. This is the change that we saw. Y stayed the same, but x got a sign change, and that's reflecting over the y-axis. And if you look at your matrix you used, it's the same one that you saw down here. And this matrix is always going to do that transformation. This is going to reflect over the y-axis. So ta-da, we have successfully reflected over the y-axis. And if you're wondering what it looks like on a graph, right, -2, 5 would be here. And then it turned into 2, 5, which would be like this. Oh, sorry, like this. Hey, that's just a reflection over the y-axis. All right, so what I'd like for you to do is pause the video and see if you can successfully transform on example 2. And we'll have you check it in just a moment. Pause the video and do it. All right, let's have you check and see how things went. Did you get 5, 2 as a resulting vector? Hopefully you did, because -2, 5 times 0, 1 is going to give you the 5 there. And then -2, 5 times -1, 0 is going to give you the 2 on the end. You can kind of look through and figure out where the numbers came from if you got a bit lost there. But we got our starting vector was -2, 5, and now we end up at 5, 2. You know, if we do a quick sketch of kind of what this looks like, 1, 2, 3, 4, 5, looking at a vector that went from here, and it went all the way over to here. Well, this is a 90-degree clockwise rotation. 90-degree clockwise rotation. And you can even check to see if it's right by looking at the top part. Let's look at 90-degree clockwise rotation. Hey, isn't that the matrix we just multiplied by? This matrix will always rotate your vector 90 degrees clockwise. All right, let's do a couple more. We got example 3 and example 4 there at the end. I want you to see if you can do example 3. So pause the video and see how things go. Get the new vector. All right, let's have you check and see how things went. Did you get -10, 25? Well, you should have. And if you did, this going from here to here is kind of a strange transformation. We haven't done this a whole lot. This is called a dilation. And what dilations do is just takes your components and your times in by a certain value and makes it that many times as big. So dilations make things bigger or smaller by a specific factor. And so it was like all of these components here got times by 5, right? -2 times 5 gives you -10. 5 times 5 gives you 25. And so this is a dilation. Whoa, that's a bad A. Dilation by a factor of 5. Awesome. So it makes it 5 times as big. And then we got our last example. This one's a little tricky. It's got numbers in here that aren't just ones, a lot like this previous one. I did want to point out in the notes, if you're looking at timesing by something, that's not one, that's a dilation. And you can combine dilation with other transformations, and that's what this note is talking about. So let's have you try it out and see what happens. Go to example 4, pause the video, and go ahead and times these together and see what happens. All right, let's have you check and see. Did you get -35, -14? Well, you should have, right? -2, 5 times these will give you the -35 on the end there, on the first one. And then -2, 5 times 7, 0 is going to give you the -14. And so these 7s in here let you know that it was a dilation by a factor of 7. 4, 5, 7. And the makeup of this, if you look at it, if you pretend these are 1s for just a moment, you can compare this with your notes here and figure out which matrix you're looking at. Well, let's see. If we pretend those are 1s, we got 0, 1, -1, 0, which is this one, which is a 90-degree counterclockwise rotation. And so our example here dilated by a factor of 7, and rotated 90 degrees counterclockwise. And there you go. Sometimes it's got 2 transformations in one, but you can deal with that. I believe in you. Good luck out there.